Any questions from anyone before we get going? Reading going okay for people? Okay. I had just a couple of sort of administrative things just to mention. The first is that I got everyone's group preferences. So if you look at the spreadsheet that we've been using in lab sections to keep track of who needs help and that sort of thing, all of the groups are updated on there, and all of the PC names are also updated on there. So if you and your group would like to meet on your own time to start working through anything, that PC and all of the equipment attached to it is yours for the rest of the semester. So you can log into your group's PC at any time for the rest of the semester. We had a small issue in last week's lab sections with some of the scopes. I got all those fixed. So for this week and for the rest of the semester, the scopes seem to be working just fine. I tested each of those, and that seems to be going okay. Had one question about someone was looking ahead at some of the recommended homework associated with Lab 1, and there are questions related to direct digital synthesis, which is the algorithm that we'll use to produce sounds in Lab 1. We have not covered that yet in lecture. Depending on the speed with which we get through material today, we'll either go through that on Wednesday or Friday. However, if you'd like to read ahead on any of that stuff, there is on the course website in the applications section, the first link in that section is direct digital synthesis. And you can open that up and take a look at it. And if you read through that document, there's sufficient information in there to do all of the homework problems. I actually wrote that web page and then did the homework. So the homework is kind of based on that web page. And that's going to be basically the resource that I'll use to talk through direct digital synthesis in lecture. So if you read through that, you'll have a good idea of the algorithm. But we will spend a whole lecture going over that one, just because it's one of these algorithms that it's worth taking a moment to talk about. It can be a little confusing. I think Bruce and I were talking about this a little bit before lecture starts. It seems to be one of these algorithms that the confusion stems from the fact that it seems too simple. So it's worthwhile just going over it in the lecture to explain it. So we'll do that either Wednesday or Friday, depending how much we get done today. Okay. If there aren't any questions, then I'll share my screen and get started. And I'll briefly remind folks where we were. So I'll start by just showing you this diagram that we've been spending the past few lectures looking at, which attempts to summarize all the hardware and software that we're using in all of our labs. So I will just very briefly remind you, there's this library of internal hardware tools that's available for you to use in your design. We configure and control that hardware with a microchip provided C library called plib. And in the last lecture, we started to see some examples of using plib to do things like open and configure an SPI channel, open timer 2 and set up an interrupt, all these sorts of things. So we were talking through plib through examples, and the specific example that we were using to talk through it is the demo code that you all got up and running last week. And what I'd like to do today is continue with that and start discussing ProtoThreads, which, as I mentioned previously, is the threading package that we use to actually organize our software. So we're writing threaded programs and we're organizing it with a lightweight threading library called ProtoThreads. And just like we did with plib, I think that this is best introduced by looking at it in code and seeing some examples. And the specific example, again, that I'm going to use to talk through this is the example code that we got up and running in lab last week. Okay, and so I'm going to talk through ProtoThreads a little bit. And then with time permitting, I'm also going to talk through this Python interface that we use to communicate with ProtoThreads. It's over a UART interface, and we'll take a look at that as well. Okay. So let me pull up the code and just briefly remind folks what we were looking at. So this is all the code that you downloaded last week to get up and running. And last time we were looking through the source file that contains the function main. I mentioned that this is the logical place to start because your code execution begins in the function main. So that's where we will start. We looked at some of the includes, and then we scrolled down past all these thread instantiations, which we'll talk about today, and took a look at main. And we talked through this in detail last time, but I'll just very quickly remind you, here in main, we used a plib function call to open a timer. We used a couple of plib function calls to turn on and configure the interrupt associated with that timer. We set an I/O port as a digital output. We configured the data line for an SPI channel, and then we opened and configured the hardware interface that does SPI transactions. And I'll very briefly mention, in either the first lecture or the second lecture, I talked about this class being very focused on hardware-software co-design. And it's a very simple example of that, but this is an example of hardware-software co-design, where on this particular chip, on the PIC32, there's a hardware peripheral that does SPI transactions. And what we're doing here is using plib to set up that hardware peripheral to do SPI transactions. The alternative here, a bad decision in the hardware-software co-design would have been to do these SPI transactions in software by bit banging, which is sort of the alternative, where bit banging is you look at the SPI protocol and in software, you toggle I/O ports to instantiate that protocol and send transactions over an SPI channel. You could do that, but instead of doing that, we're saving ourselves CPU software cycles by offloading that transaction to this hardware peripheral. So we set up this hardware, and now what this will allow us to do, we'll see this today, is drop a packet into a transmit buffer. This hardware peripheral does that transaction and then lets us know when we're finished. And we just wait for it to tell us that we're finished. So this is a very simple example of a good hardware-software co-design decision, right? Is using this hardware peripheral to do these SPI transactions. We then built some sign tables. As I mentioned last time, I'm going to save discussion of this for the direct digital synthesis lecture, either Wednesday or Friday. Enabled system-wide interrupts. Did a few function calls associated with the TFT display screen. You can look at the instantiation of these in the TFT header file. But we instantiate the screen, do a couple of instantiation function calls, fill the screen with black, and then set the orientation. And then down here below, we set up the threader by calling the PT setup macro. We add a bunch of the threads that we instantiate farther up in this code that we're going to look at today. We add those to the threader. Initialize it by calling another macro. Tell it that we want to use round robin scheduling. By it, I mean the scheduler. We're telling the scheduler we want to use round robin scheduling. And then we call the PT schedule macro, which starts the scheduler and starts scheduling all of these threads. So in short, that's what we looked at last time. And what I want to start with today is by looking at the instantiation of some of these threads. And I'll start specifically with the thread. As I mentioned, one of the advantages of threaders like this is they're highly modular. So if you look at one thread, you basically understand all of them, right? So I want to start by looking at a simple one, which is the thread associated with buttons. And then we'll look at a couple of the other ones as well. So you can see that one of the threads that we're adding to the scheduler is this one called ProtoThread buttons. Let's just scroll up and take a look at how that particular thread is instantiated. And it is instantiated here. So this is the thread ProtoThread buttons. As I mentioned, each of these threads is essentially a completely separate execution environment. So each of these threads contains an infinite while one loop that it never exits from. And what the scheduler does is move from one of those infinite while one loops to another one of those infinite while one loops that's contained within another thread. And it does those context switches when you tell it to in software. So a particular thread will continue to run until it yields. You decide when it yields. And then when it does yield, the scheduler will look at the next thread and say, are you ready to run? And if it's ready, then that one runs. If not, then it goes to the next one. And it goes through all of them and then goes back to the first. That's what the round robin scheduler is, right? It's just asking, are you ready? Are you ready? Are you ready? And when it finds one that's ready, that one runs until it yields. And then the next one will run. It's up to you to decide when those yields happen. But let's take a look at this. So this whole threading package is defined by C macros. And later on in this lecture, we'll look at the header file that defines these C macros. But we instantiate this by calling a C macro called PTThread. As an argument, this macro takes the name of the function that instantiates that thread, and it takes the arguments of the function that instantiates that thread. So in this case, the name of the function that instantiates this protothread is ProtoThread_buttons. We could have called it something else, but that's what we've called it, ProtoThread_buttons. And the argument to this thread and to all of the other ones that we instantiate is, this is one of those kind of C gibberish statements, but this is a pointer to an object of type PT. And this is a type that is defined in the ProtoThreads header. It's the ProtoThread control structure. But this argument is going to be the same for all of the threads that you instantiate. You'll change the name for each of the threads that you instantiate. But we're calling a macro, and as an argument to that macro, we're passing a function called ProtoThread_buttons that as an argument takes a pointer to an object of type PT, ProtoThread control structure. The next thing that we do is define this function. That's what's contained down here below. And a lot of this, there are a few sort of ProtoThread macro calls that we'll talk about, but most of this is very normal looking C because most of it is just normal C. But you can see that within this ProtoThread function definition, the first thing that you see is a call to a macro called PTBegin. Probably all of your threads will start with PTBegin. This is how you indicate the beginning of the thread. And it will probably be the first line in every thread that you instantiate. If you have anything before PTBegin, then according to the documentation, anything that's before this will get run every time the thread is scheduled, which probably you don't want, right? So probably every time you create a thread, the first line in that thread will be PTBegin. This is paired at the end of the thread with another macro call called PTEnd. And in order for this to compile correctly, you need an end to be paired with a begin. So you mark the beginning of the thread and you mark the end of the thread. Now you'll notice, okay, that this PTEnd lives outside of the while one loop contained within this thread. So this line will actually never get executed, right? We don't want for this thread to actually ever terminate. We just want for it to yield and then to run again. And when it yields and when it runs is up to you, and it'll be scheduled by the scheduler. But you can see that this PTEnd is outside of the while one loop, so it will never actually get run. But we need to have it in order for this to compile correctly. We need the end paired with the begin. And then everything else in here is very normal looking C. So you can see we do a few things before the while one loop that will only run the first time that this thread gets scheduled. And in particular, what you see is we set up port A bit 0, so pin A0. We set that up as or we clear it, which is to say if it's at a high voltage, we pull it down to a low voltage. And then we set it as a digital output. It turns out that the onboard LED for these big boards that we're using is at port A0. So we are turning off the LED in this line, and then we're configuring that particular I/O port as an output in the next line. And then we drop into this while one loop, and this is the loop from which we never exit, right? So you can see the first thing that happens is that this thread yields until some logical condition is met. So what this means is the scheduler, as it loops through threads and asks, are you ready to run? Are you ready to run? Are you ready to run? This particular thread will say it is not ready to run. It will yield until this variable called new button is equal to 1. We're going to see where this variable is set in a moment. It turns out this is set in another thread. But for now, what's happening here is this thread is saying, I'm not ready to run until new button is equal to 1. When the variable new button is equal to 1, then it will, when the scheduler loops back to it, it will say, actually, I am ready to run. And then it'll execute the rest of the thread. Okay. And then what happens in the rest of the thread is it takes one of a few possible actions depending on the values of a few global variables. So the first thing that it does is it sets that new button flag back to 0 so that when it loops back to the top of this, it won't just continue to run. It will only run again when that flag, which is being set elsewhere in the code, is set again. So it clears that flag. And then it looks at the values of a couple of other global variables. These two, we're going to see where these are set in a moment. They're set in another thread. But if these variables button ID and button value are both set to 1, the button ID is telling us which button in the user interface was pushed. The button value is telling us whether it was depressed or released. So this is saying if button ID 1 was pressed and if its value is 1, which is to say it is depressed, then it sets bit A0, which is to say it turns the LED on. So in the example code that you all ran this week, there was a button at the top of that interface that said LED. Turns out that was the button with button ID 1. And you'll recall that when you press that button, the LED turns on. The logic that causes that to happen is right here, right? This is saying if the LED button was pressed, button ID 1, and if it's depressed as opposed to released, then we set that bit. If alternatively, the action that the user took was still associated with the LED button, but instead of being pressed, it was released, which is to say button value is equal to 0. We're going to see this, how this is set again, like I said in a moment. Well, then we turn the LED off. And this, you'll recall, when you release that button, the LED goes off, and when you press it, it goes on. So all of that logic is happening right here. And then the only other possible action that's being taken here is, you'll recall that in that user interface, there was a clear screen button. And in the case that the user has pressed that button, then it calls the TFT fill screen function defined in the TFT header file to make the whole screen black. So it'll wait until this variable new button has a value of 1. It then sets the value of that variable to 0, takes one of these actions, depending on the value of these other global variables, and then it'll loop back up to the top and wait again until another thread sets this variable new button back equal to 1. Questions about this? Okay. So if we look at some of the other threads, sorry, did someone have a question?
I had a comment, and that is that the Python design is that it generates a button event on every press and every release.
And when we look at the Python code in a moment, I'll point out the lines where that configuration is set. Turns out if you don't explicitly say there's an event associated with press and release, then you only get events thrown on presses and not releases. But it's sort of a small thing that we'll point out when we get to the Python code. But if we look at some of these other threads, you'll see that structurally, they are basically the same. So we just looked at this ProtoThreads button. We can now look at the thread associated with toggle buttons, which are the check mark buttons that you'll remember from the user interface. And you can see, as before, we define this thread by calling the PTThread macro. The argument to that macro is the function which is going to instantiate this thread. We're calling this one ProtoThread toggles. Generally a good idea to keep the same sort of rules for naming these threads. It makes your code a little less error prone. So we're using the convention where it's ProtoThread underscore and then some word associated with the event in this thread. So in this case, it's toggle buttons. And then as before, the argument to this function is a pointer to an object of type PT, the ProtoThread control structure. And then we instantiate this thread. Just like before, the thread starts with a PT begin that marks the beginning of this thread. It ends with a PT end, which marks the end of this thread. This PT end is outside of the while one loop. So this line of code is never actually executed, okay, but it's paired with the begin. And then in this thread, we declare a variable of type short called circle color, and we're setting that equal to red. This ILI 9340 underscore red, there are a few colors, like I mentioned last time, that are defined in the TFT header file. So instead of putting the 16-bit RGB value associated with red, if you'd like, you can use these these variables which are defined in that header file for things like red and blue and black and green and that sort of thing. And then we drop into the while one loop. And this thread, as the other one, it has to tell the scheduler when it's ready to run and when it's yielding. In the previous thread, we were yielding until a logical condition was met. We were yielding until the variable new button was equal to 1. In this case, we're doing something slightly different, which is we're yielding for a particular amount of time. So in this case, this thread is going to yield for 100 milliseconds. And then after 100 milliseconds have expired, it will run. And when it runs, very similarly to the button thread, it looks at the value of a few global variables and then takes different action depending on the value of those variables. If new toggle is equal to 1, which is to say a toggle button was pressed, then it clears that flag. It determines which toggle button was pressed and whether it was checked or unchecked, and then takes different action depending on which event took place. So if toggle button 1 was pressed and it was checked, then it turns the little circle on the TFT display screen from red to green. This was the dot color check button in the user interface that you all were playing with this week, right? So you'll recall that when you checked that button, the little circle on the TFT display screen turned green. This is where that logic is. And when you unchecked it, it turned red. And if after 100 milliseconds, no toggle button event had taken place, then it just redraws the circle with the same color. Okay. And then it loops back up and it waits for another 100 milliseconds until this runs again. Okay. Any questions about this? So you can see that it's structurally very similar to the previous thread that we look at. And in fact, any of the threads that we look at are structurally very similar. It's one of the advantages of this. All that changes is the logic that is within the thread and the conditions that have to be met in order for that particular thread to be scheduled, right? So in the button thread, this was a logical condition. In the toggle switch thread, this is a certain amount of time having expired. It might alternatively be a semaphore. You might have this yield until some other thread throws a semaphore and then it'll run. So you have a few options for controlling how these context switches take place, but you need to be careful about how they take place. Other questions? Okay. So we could look at others of these threads, and for most of them, we would find that they look basically the same. I want to draw our attention to one in particular, which is a little bit different, and that is perhaps, I think, important to consider because you're going to have a thread like this one in every project that you create, in every lab that you do this semester. And this is the thread associated with serial communication. The reason that you're going to have a thread like this in every one of your projects this semester is because we're interacting with all of your labs through a UART interface, right? The Python that's running, the Python user interface that's running on the lab PC communicates with the PIC over a serial interface. So a thread like this one will be in all of your projects to handle that communication. It's a little bit different, but structurally it's pretty much the same as the ones we've just looked at. As before, we instantiate this thread with a call to the PTThread macro. This macro takes the name of the function which instantiates that thread. In this case, it's ProtoThreads serial. And the argument, as before, is a pointer to an object of type PT. And then as before, the thread starts with a PT begin and ends with a PT end. And then in between that begin and end, we instantiate the logic that's actually contained within this thread. We declare a junk variable. We'll see how this is used in a moment, but we just declare a variable before the while one loop. And then we drop into the while one loop. The first thing that happens in this loop is we declare a few variables. The first one's called PT terminate character, PT terminate car. This too, we'll see how this is used when we look at the ProtoThread header file. But this is, we are marking the end of a serial transmission from the Python interface with a carriage return character, \r. So this is the character that we're using to separate separate packets. It's defined here. And we define a couple of other variables, terminate count and terminate time, which are both set to 0. I would recommend keeping these set to 0. This is just allowing you to change some configurations about how you decide the beginning and ends of packets. We're going to be using terminate characters, basically, in this class. If you want to change this stuff around for a final project to try to do something a little exotic, then that would be fine. But generally speaking, this will be configured as shown. This next line, which for the moment I'm going to kind of wave my hands at, but we're going to come back and revisit it. This next line spawns a new thread called get machine buffer. We'll look at the definition of this thread in the ProtoThread header file in a moment. But for the time being, I want to talk about the consequence of this thread, and then we'll save how those consequences are achieved for just a moment. But what this thread is doing is taking the contents of the UART receive buffer and putting it into a character array called PT term buffer. So this thread will sit and yield on this line until it receives a serial transmission from the Python interface. When it receives that Python transmission from the serial interface, the action that it will take is to take the packet that was in that UART receive buffer and put it into a character array called PT term buffer. So after this line is terminated, whatever the Python interface sent us, it's now available for us to look at in this character array called PT term buffer. And as I mentioned, we're going to look at how that happens in just a little while, but I want to stick to this level of abstraction for the moment so that we can talk through this thread, and then we'll pop down and look at the details of this. But phenomenologically, what's occurring here is this line is getting the contents of the UART receive buffer and putting it into this character array. And then all that happens for the rest of this code is we look at the contents of that character array, which is to say we look at the packet that the Python interface sent us, we parse through it, and we take different action depending on what we see in that buffer. So when we look at the Python code, we're going to see this explicitly, but we are using a communication protocol between Python and PIC, where the first element of that character array is going to be a letter, a character letter represented in ASCII code that tells us what type of event took place. Was it a button push? Was it a toggle switch? Was it sliding a slider? Did the user send text in through the input window? What kind of event took place? That information is contained in the first element of this array. So for example, if the value in the 0th index of the PT term buffer character array is T, then according to the protocol that we're using, that means a toggle switch was pressed. And then we look at some of the subsequent elements of this character array, and that contains some clarifying information about which toggle button was pressed and what's the value of that toggle switch. So it's going to be a letter that represents the type of event, followed by a sequence of numbers, 0 through 9, that add clarifying information about that event in a way that I'm about to explain. So in this case, say a toggle button was pressed. The first element is a T that says this was a toggle button. We then look at elements 1 and 2, and we use these two elements to tell us which toggle button was pressed. And as defined, it could be any toggle. You could have up to 99 toggle buttons in your user interface, and this would work. This is a little C trick that maybe needs just a little bit of explanation. But the protocol that we're using is the element of the first array. Say toggle button number 45 was pressed. Okay, so that's toggle button 45. 4 in the tens place, 5 in the ones place. The protocol that we're using is the tens place digit goes in the first element of the character array, and the ones place digit goes in the second element of the character array. And we want to put the value 45, which is to say the 45th toggle switch, into this toggle ID. So the way that we do this is to take advantage of the fact that in ASCII code, the codes associated with all numeric digits are sequential. So the ASCII code associated with the digit 0 turns out to be 48. You could look that up in an ASCII table, and that's what it would tell you. The ASCII code associated with 1 is 49, with 2 is 50, with 3 is 51. They're sequential. What these single quotes do in C, if you put a character inside of single quotes, what it returns is the numeric ASCII code associated with that character. So in this case, single quotes 0 is actually giving us the ASCII code associated with 0, which is 48. And because all of these ASCII codes are sequential, 48, 49, 50, etc., if we take the value in the first element of the character array, which, as I said, represents the tens digit, so this will be the ASCII code associated with some digit. I think I was using the example 45. So this will be the ASCII code associated with 45, which will be 0s 48, 49, 50, 51, 52. And we subtract the ASCII code associated with 0, which is 48. The difference between those two ASCII codes is the actual numeric value that we're representing with that ASCII code. In this case, 4. And then because this is the tens digit, we multiply it by 10. And we add to that the contents of the second element of this character array minus the ASCII code associated with 0 to get the ones digit. So in this case, this would be the ASCII code associated with 5 if this was toggle switch 45, minus the ASCII code associated with 0. That difference gives us the value 5, and we add that to what we got from the tens digit to tell us which toggle button was pressed. Does that make sense?
100 quick question.
Yeah.
I might have missed it, but did you explain the contents of the function call to PT spawn or the macro call to PT spawn?
I didn't yet. I said I was going to wave my hands at that for the moment so that we can stick to just considering this thread for now. And then we'll pop down and look at how PT spawn actually puts the contents of the UART receive buffer into this character array.
Okay, sure. Thanks.
Yeah. I think that's the way to do this with the least confusion. I could be wrong, but I think it makes sense to stick with this level of abstraction, and then we'll pop down and see how this stuff actually takes place. So that is how we establish which toggle switch was pressed. And then we want to establish whether that was checked or unchecked. And we keep that information in the third element of this PT term buffer character array. And as before, we subtract. This will be, turns out this value will actually be 0 or 1, 0 for unchecked, 1 for checked. And when we subtract the ASCII code for 0 from the ASCII code for 0, we'll get 0. When we subtract the ASCII code for 0 from the ASCII code for 1, we'll get 1. So if this was pressed, toggle value will assume the value 1. If this was unpressed, or unchecked rather, toggle value will assume the value 0. Does that make some sense? If you pull up an ASCII table after class and look at the codes, I think this will start to click for you. This turns out this is an older trick than I realized. I didn't see this trick until I was looking at, Bruce wrote this particular example code, and I hadn't seen this before. And then partly out of interest and partly out of just historical curiosity, I've been going through this C programming book. Maybe some of you guys have played with this before. But in the first examples, they pulled this trick. So it's an old one. Okay. So that's what happens in the event that the first element of the character array is a T, which means toggle switch. In the event that the first element of the character array is a B, which in our case means button, then we do basically the same thing. We set the flag new button to 1. recall, this is the flag that we were using to run the button thread, right? So that button thread was yielding until a logical condition was met, and the logical condition that it was waiting on was the value new button to be equal to 1. This is the other thread that sets that flag. So in the case that this serial thread receives a button press, it will set the new button flag to 1, and then it'll use the same trick to determine which button was pushed, and was that button pressed or released. So it's setting the new button flag, and then it's setting the button ID and the button value. And let me just briefly scroll back up to the button thread that we already looked at, just to remind you how these things were used. So if we scroll back up to the button thread, you will recall this thread was yielding until the new button flag was equal to 1. So it's waiting until a button was pressed. It clears that flag, and then it takes different action depending on which button was pressed. And we just saw where this value is set, right? It's set in the ProtoThreads serial thread and the value of that button. So that's the logic associated with buttons, and that's that same logic maps to essentially every other element in that user interface. The thread associated with toggle switches is doing something extremely similar to this. The thread associated with sliders is doing something very similar to this. It's very modular, right? So if we can understand how one of these things works, it's basically how all of them work. But okay, so in the case of a toggle switch, we do these things. Buttons, we do the same sorts of things, just setting different variables and different flags. The only thing here that's slightly different, perhaps, is the slider. In the case that we receive a slider value, we fill our slider ID and slider values using an scanf as opposed to looking at the individual elements. But it's the same outcome, right? In the case that we get a list box item, then we set a new list flag, which will trigger the thread declared elsewhere associated with list box items to run. And then we set 2 variables associated with which list item was selected and what's the value of that list item. And the same essential thing for the radio groups. And in the case that the user sent a string through the text input, then we set a flag, which means there's a new string received from the user. And then we copy that string. We copy the contents of PT term buffer, which contains the user inputted string, into a character array that we can use elsewhere in the string processing thread to do something interesting with that string. So we're copying the contents of PT term buffer into a separate character array called receive string. And if we were to scroll up and look at the thread associated with string inputs, let's see, toggles, buttons, ProtoThreads string, you can see we're yielding until the new string flag is set. Then we're clearing that flag, and then we are looking at the contents of that receive string character array into which we've copied the contents of PT term buffer and taking different action based on what we see in that character array. In this case, the logic here is being used to do things like change the direct digital synthesis frequency, or change the DAC voltage or these other sorts of things. You might have other logic in here, but essentially that's all that's happening. Is in the case that a string is received, we set the string flag, we copy the contents of the UART receive buffer into another character array called receive string, and then we look through that string and take different action based on what we see. Okay. Any questions? So like I said, in almost all of your, well, in all of your lab sections, you will have a thread like this. It might not contain all of these options. Maybe your user interface only has buttons and a slider, in which case you might not have logic associated with toggle switches or with list box items or these sorts of things. So you might have a pared down version of this thread in your lab, but you'll have a version of this thread in all of your lab that's receiving input from the Python user interface. And the Python user interface is the next thing that I'm going to pull up for us to take a look at, because it makes sense when considered in combination with this serial receive thread. Okay, questions? Okay, in that case, I'm going to go, I need to download the Python code, which is available on the Day Zero webpage. If we scroll down and take a look at this Python code. Oops, internal server error. That's no good. Just a moment. We'll get that link fixed. But it's also available on the remote access interfaces page. If we look here, internal server error. Just a moment, sorry. Okay, sorry, we might have to delay the conversation about the Python script for until next time, just until we can get this link fixed.
It's not broken, it's just that some browsers won't download Python because they consider it executable.
Okay,
so
let me try.
You have to right click it and save.
All right, let's see. Okay, thanks, Bruce. Oh, damn, hold on.
No, that's an internal server error. It's nothing about executable code.
I will tell you, that's what Windows throws when you try and download Python. I don't know why it throws an internal server error, but that's what it does. The very same, I can read the very same file from an iPad just fine.
Interesting, okay.
Or from a Linux machine. So I have no idea why it's tricked up that way.
That file, I can mail it to you if you want.
But you can just again, right click it and you should download it.
All right, let me take a look. No luck.
So interesting.
So
I have a copy of the oscilloscope demo with Python. If you want me to email that to you real quick.
here, I can open it up. I have it open on my other PC here. In any case, sorry about that, folks. Okay. This is the Python code that you all got up and running in class this week. And I want to just briefly talk through this. So this is setting up, and then this is setting up the user interface, and then sending UART, sending serial packets to the PIC depending on what the user did in the user interface. So we import a couple of libraries here, time and serial. And then we open the serial port connected to the microcontroller. And this is the line that you all modified in lab this week, right? So you had to look up which port was the PIC connected to, and you had to make sure that the baud rate as specified here agreed with the baud rate as specified in the config.h file. The next thing that happens here is we build the user interface itself. And the way that PySimple GUI does these user interfaces is each row of the user interface is set up as a list. So the user interface in Python, the layout for the user interface looks like a list of lists, just sort of a very Python-y way to do this. But if we look at a particular list, then we can see what is contained within that row of the user interface. So in the first row here, you can see that all that we have is some text that says LED control. In the next row, which is the next list, we have the first actual interactive element of this user interface, which is a real-time button. The first argument here is the text that appears on that button. So the text that appears on this real-time button is LED. Importantly, we give this element of the user interface a key name. It's important that you follow the specifications for naming your elements as defined in the comments above, because we parse through these key names in order to send the clarifying information about what event took place through serial to the PIC. In the serial receive thread that we just looked at, you'll recall that we parsed through the receive buffer and looked at a few elements in that to see, for example, which button was pushed and what's the value of that button. That information is extracted from the key name. So if you name things differently than the convention that we've decided upon, you might have to change things around. But in this case, we give this particular button the key name pushBut01. If we wanted to add another one, like we do here, we would give it the name pushBut02. So the naming convention associated with buttons is pushBut and then two digits representing what number button that was. So this particular button interface, it has some clarifying text on it. It has a key name, and we specify things like the font. The next row of the user interface has some more text, followed by another button. This one, the text on this button is clear LCD. Its key name is pushBut02, and then there's some font settings. Also in this row, you can see that we're still in the same list here in Python. We haven't closed our square bracket yet. We also have a checkbox item. The clarifying text on this checkbox is .color. It has the key name toggle01. We set some font settings. And then importantly, for every graphic user interface that isn't a push button, we have to say enable events, which is to say if the user interacts with this element, we want for an event to be thrown that we interpret as an interaction with the user interface. Some more text for line position, a slider. You can, and you know, I perhaps won't talk through every single field in all of these. The PySimple GUI is quite well documented, so you can read through these if you'd like. But many of them, like most Python stuff, is pretty easy to understand. So when we set the slider, we set the range of that slider, the default value of the slider, the size of it. We give it a key name, an orientation, a font, and then enable events, and so on and so forth for a whole bunch of other items in our user interface. I think I'm going to stop for now. Yeah.
I just looked through the, it turns out that the server, remember the server changed about a week ago or 2 weeks ago. The server I brought this stuff up on the first time would serve the files even though it threw an internal error. The new server doesn't serve them at all. Okay. And so I'm going to have to rename them something besides PY.
Maybe .py.txt or something. And folks will just have to remember to change the extension.
That's just so horrible. I apologize, Alex. You're quite right. But I don't know why. I mean, I suppose I could try and get them to change it, but I'll just change the extensions on the files. It's so ugly, but okay.
This is interesting because your comment about working on a Linux machine works because I visited that same link on my Linux machine and it worked. So it's
it did.
problem on Mac OS and maybe Windows. I don't have a Windows machine right here to test on.
Now I'm really confused. Actually, it turns out I was testing it though at that time on a Linux machine also. So I'll add a TXT extension to everything with the understanding that when you run the program, you're gonna have to strip that off.
Okay.
Sigh. Sorry.
Thanks. Okay, well, at least we caught it now and before lab section. So we're out of time for today, so I'll see some of you in lab this afternoon. If you guys look at the lab spreadsheet, you will see that the Monday lab is pretty sparse. There's 2 groups in the Monday lab, 4 groups in the Tuesday lab, and 6 groups in the Wednesday lab. So if anyone is in the Tuesday or Wednesday lab and they want to come to, you can come to any lab you'd like, right? And if you're in a crowded section, perhaps you want to come to a less crowded section and that would be fine, or not, and that's also fine, but just extending the invitation.
In terms of the lab, the zip file should be completely readable and have the code in it also. And that should download just fine.
Any questions from anyone? Okay.